Hello everyone. Today we will provide a brief overview of our project. Our initial goal is to gain a deep understanding of developing autonomous AI algorithms within the context of the Azul game. The second goal is to implement and explore three different techniques to play for this game. We aim to evaluate their effectiveness, strengths, and limitations. Ultimately, our overarching goal is to achieve success in the game itself. Before diving into the different techniques we plan to experiment with, it is crucial to consider the characteristics of the problem at hand, because there is no one-size-fits-all AI techniques exist. Firstly, although Azure can accommodate multiple players, our task specifically focuses on a two-player game. Also, the problem is adversarial, wherein both players strive to maximize their individual scores. Thirdly, the actions within each round are deterministic. For a given state S, action A will consistently result in the same successive state S prime. However, the game state at the beginning of each round is stochastic, which is influenced by the randomized row of tiles drawn from the back. Players first prioritize completing patterns line to gain marks, as well as keeping space available for tile placement in later rounds. The other priorities include creating complete columns and sets on the pattern board for end-of-game bonus points. Moreover, creating cluster patterns on the board leads to higher marks for end-of-round increments.
We initially explored a heuristic-based approach. It prioritizes immediate gains and disrupts opponents' strategies, while also considering counter strategies through minimax principles. There are three main challenges. Heuristic function is carefully considered by potential scores, adjacency bonuses, and the formation of complete lines, which prioritized high scoring and advantageous steps. To manage the large state space and action space, we filtered actions for less penalty. Moreover, choosing the goal state was based on maximizing the heuristic score to align with the objective of achieving the high score within the round. The primary objective for minimax is to maximize their own scores, while simultaneously minimizing the opportunities for their opponents to succeed, based on the self-defined evaluation function. However, the extensive range of possible actions can lead to challenges in terms of time complexity and space complexity. Techniques such as filtering actions, alpha-beta pruning, and iterative deepening are employed to mitigate these challenges. Another challenge lies in the highly deterministic nature of the evaluation function and the assumptions made about opponents' actions, which can occasionally lead to suboptimal decision-making. Multi-color tree search, abbreviated as MCTS, is a popular and effective technique for developing artificial intelligence agents in games. In MCTS, the agent gradually builds a tree-like structure by simulating random gameplays and evaluating their outcomes. By exploring different paths in the game tree, the agent can estimate the potential outcomes of each action and select the one that maximizes its score. MCTS is suitable Azul because its anytime algorithm nature allows MCTS to return the current best action within the given syncing time. In addition, MCTS is simple to implement with a heuristic algorithm that can operate effectively without domain-specific knowledge beyond the game rules and end conditions. However, there are challenges that we may face when applying MCTS, such as the high branching factor, exploration and exploitation trade-off, the lack of iterations, dynamic and uncertain game state, and agent modeling. Next, we will give you a demo to show the operations of our agent in the game.
Both the evaluation function using the minimax algorithm and the heuristic function employed in the greedy best-first search algorithm take into account the annual run increment, floor penalty, agent bonus, and pattern line completion scores. Agent 0, the greedy approach, prioritizes completing columns and sets based on the end-of-game pattern. In contrast, Agent 1 implementing the minimax algorithm places higher emphasis on the end-of-run increment points, consider them as a higher weight that reflect cluster patterns, particularly evident in the end of round 3. However, the minimax algorithm adjusts the subscore weight based on the current game score, which can result in a failure to complete any pattern successfully at the end of game. Greedy algorithm occasionally exhibit short-sighted behavior, primarily focus on immediate gain by completing pattern line without considering the potential point that could be obtained by filling the lower pattern line. Furthermore, context information is not taken into account. For example, an action may involve placing 2 red tiles on the second pattern line instead of the fourth. This decision could lead to 2 consequences. Firstly, assigning the same color to different lines occupy space intended for other color, potentially resulted in significant penalties. Secondly, without considering the availability of red tiles in the factory, the fourth pattern line may not be complete as desired.